Hello everyone, I am Meenakshi Chauhan and in this video I will be discussing about IEEE standard for floating point numbers. In this video I will be discussing about floating point numbers, single precision representation of floating point numbers, double precision representation of floating point numbers and spatial values representation. So let's get started. Before studying this lecture, students are strongly advised to study the lecture on number system, how to convert a binary number into decimal and how to convert a decimal number into binary. In this lecture, we will look at how a real number or a fractional number can be represented in a computer system. Floating point representation. A number may have a binary or decimal point. The position of binary point always describes whether the number is an integer number or a fractional number or a mix of integer or fractional number. As you can see here in this example, this number denotes the number is a fractional number. The position of a binary point is at the left. Here the position of binary point is at the right. So you can say that the number is an integer number. And this example is denoting that the number is having integer part and fractional part. Here B is a binary digit because we are talking about binary number. So we will have binary digits, either 0 bit or 1 bit. The representation of binary point, or we can say decimal point, is characterized by the position. So according to the position of a binary point, we have two ways of representing binary numbers which are having binary point. We have two methods. One is fixed representation method. Second is floating point representation method. So let's start with fixed position method. Here we are representing real numbers in computer. So we have two methods to represent real or fractional numbers into computer. One is fixed position method. Second is floating point representation. Fixed representation or floating point representation is all about the position of binary point in a number. So fixed point representation method. In fixed point, the binary point position is always fixed. The position can be at left or at extreme right. In this method, the position of binary point is kept fixed. The point can be at extreme left of the number or it can be at extreme right of the number. In the either case, binary point is not actually present. We do not store the binary point into registers, but its presence is assumed from the fact that number stored in register is treated as a fraction number or an integer number. As we have looked at the examples of how position of a binary point defines whether the number is an integer or a fraction or a mix of integer and fraction. So the number stored in a register is a fractional number or an integer number. It will be defined by the position of binary point. This method is not flexible because we have fixed the position of binary point and we have limited capacity of registers, so we can represent up to a limited range of numbers. This method is not flexible or it cannot represent very small or very large number. In scientific calculations, mostly very large or very small numbers are used. So fixed point representation method has the limitation that it cannot represent very small or very large real fractional numbers. So we have another method, floating point representation. In fixed representation, the position of binary point is kept fixed. But in floating point representation method, the position of binary point is set to float. Or we can say the position of binary point is variable. It floats as the computation proceeds. So the position of binary point is variable and the number are called floating point numbers. The numbers represented where the position of binary point is a variable, those number will be called as floating point numbers. IEEE Institute of Electrical and Electronic Engineers provided a standard for floating point representation, and this standard is called IEEE 754. Actually, or in real computers, a real or fractional number is stored according to the IEEE 754 standard. Floating point representation. In this representation, any number can be represented with the help of three fields. One is sign, which denotes the sign of the number. Sign whether the number is positive or negative. Next field, significant or mantissa. Third is exponent part of the number. So any number can be represented in this form. Plus minus sign of the number, S for significant of the number, B is the base. Here we are talking about the binary number. So base is 2 and to the power exponent. And exponent can be positive number or a negative number. So we have three fields to represent a fractional number into floating point representation, and these three fields are sign field, significant or mantissa part, and third is exponent part. Here binary number system, the base is always 2. So we do not need to store base to represent floating point number because base is implicit and it is same for all the binary numbers, and this base is 2. Floating point number representation. In this, any floating point number can be expressed in many ways. As you can see in this figure, all three values are equivalent. 0.110 into 2 to the power 5 is equivalent to 110 into 2 to the power 2. Or we can write it as 0.0110 into 2 to the power 6. So all three quantities are equivalent. So we have many ways to express a floating point number. So we should have some mechanism to simplify operations on floating point numbers. It is required to normalize these numbers. So we have to normalize these numbers, and we have normalized form like this. We can say that in normalized form, the most significant bit will be non-zero. And here we are talking about binary numbers. So binary numbers have either 0 bit or 1 bit. So 1 is a non-zero value. So in normalized values, 1 will be at MSB, or we can say most significant bit. Here B is denoting binary digit and this part is called mantissa part. In normalized number, the most significant bit will always be 1 in case of binary numbers. So we do not need to store this 1. So it is unnecessary to store this bit. Rather, it is implicit. So what does it mean? We can represent a single floating point number into many ways. So we should have mechanism to normalize these number. So we have some normalization method and we will normalize the number. Then we will represent this number into floating point representation. So normalized number is one in which most significant digit of significant or mantissa is non-zero. In base 2, in a normalized number, the most significant bit of the mantissa is 1. The typical convention is that there is one bit to the left of the radix point. Here, only one bit to the left of radix point or binary point. A normalized non-zero number is one of the form like this. So, plus minus the sign of the number, 1 point, any combination of bits, or we can say it is the mantissa part or significant part into 2 to the power plus minus exponent e. So this is the normalized form of the number. IEEE 754 format. For representing floating point numbers, IEEE provided a standard for representing floating point numbers. IEEE 754 defines both a 32-bit long representation or a 64-bit long representation. 32-bit representation is called single precision and 64-bit representation is called double precision. In single precision, any floating point number is represented in 32 bits, and these 32 bits are divided into three parts. One is sign, second is biased exponent, third is mantissa. One bit is used for sign bit. The bit can be 0 or 1. 0 bit is representing the number is positive and the 1 is representing that number is negative. So 0 for positive number and 1 for negative number. Next, 8 bits are used for representing exponent, and in this we are using biased exponent. Exponent is used in biased representation, and the bias value for 32-bit representation is 127. Next, 23 bits will be used to store mantissa or fraction part. So left bit will store sign, next 8 bit will store the exponent, and exponent will be in biased representation, and remaining 23 bits will be used for storing mantissa and significant part. 64-bit representation is called double precision format. In this method, 64 bits are divided into three parts. One is sign, as same as before, sign bit. Next, 11 bits are used for biased exponent, and bias value for 64-bit representation is 1023. Next, 52 bits are used for mantissa or fraction part. So in double precision, 64 bits will be used. First bit will be used for sign bit. Next, 11 bits for exponent, and the rest 52 bits will store mantissa or significant part. So bias, as we have discussed that exponent is stored in biased representation. In single precision, 8 bits are used for biased exponent. So 8 bits can have 256 values, or we can say 8 bits can represent total 256 value, as 2 to the power 8 equals to 256. So the range will be 0 to 255. With the bias of 127, the true exponent value will be in range minus 127 to plus 128. The true exponent of a number can be in range of minus 127 to plus 128. But as we have seen that total 256 value can be represented by 8 bits, but exponent having all zeros or exponent having all ones are used to represent some special values. Only range is from 1 to 254. The range is 0 to 255, but we are excluding all zeros and all ones. So the exponent values can be in range of 1 to 254. Same in double precision, 11 bits are used to represent biased exponent. Total values represented by 11 bits will be 2048. 2 to the power 11 equals to 2048. So range will be 0 to 2047. With the bias of 1023, the true exponent values can be in the range of minus 1023 to plus 1024. For exponent values, we are excluding all zeros and all ones. So total true values in bias exponent can be in range of 1 through 2046. We are excluding two values represented by all zeros and represented by all ones, because all zeros in exponent value and all ones in exponent field are used to represent special values. Exponent is calculated according to the following equation. So biased exponent will equal to true exponent plus bias, and true exponent will be calculated as biased exponent minus bias. Now let's see the example of representing any number into single precision or double precision representation. So we have this number and we have to represent this number into single precision representation. So we have this decimal number. First step is to convert this decimal number into binary. Refer the lecture on number system and see how to convert the decimal number into binary. Then we will have the binary equivalent to this decimal number. We have this binary value. Now second step is to normalize this number. For normalization, we will move this binary point to this position, or we can say right to the leftmost one, and we will move this binary point up to 10 position. So whenever we move binary point to the left, the positive pass will increase. Whenever we move binary point to the right, the negative pass will increase. The normalized number, we have this. We have moved this binary point up to 10 position, then we will write it 1.001101000100001 into 2 to the power plus 10. Now we have 1 point. This part will be mantissa part. So 1 point m. We have 1 point m into base to the power e. So we have mantissa part this and exponent part plus 10. Now the next step is to calculate the biased exponent. Biased exponent will be equal to e plus bias. For single precision, the bias is 127. We have true exponent plus 10, bias 127. So we will have plus 137. Now we will convert this number into binary. As you can see here, the number is a negative number. So sign bit will be 1 to represent negative number. So sign bit will have 1, denoting the number as negative number. We will copy this bias exponent here, as we have calculated biased exponent this. Now we have mantissa part, and the mantissa part will be copied into the mantissa field. Mantissa filled in 32-bit representation is 23-bit long. And in this case, we will add zeros to the right of mantissa to make this mantissa filled up to 23 bits. So in this example, first we converted this decimal number into binary number. Then we normalized this number by moving binary point to the right of leftmost one. Next, we will calculate the biased exponent and then we represented this number into single precision representation. Next, we have to represent this number into double precision representation. The same steps will be applied here, as first we will convert this number into binary. Next, we will normalize this number and calculate the biased exponent. But in this case, the bias for 64-bit representation is 1023. We have biased exponent 10 plus 1023. Now we will convert this number into binary. As number is negative, so sign bit will be 1. We will copy this exponent in this biased exponent field. We will copy this mantissa part after binary point part. This is the mantissa part. We will copy this mantissa part here. And we will add some zeros to make it up to 52-bit long, because the mantissa part in 64-bit representation is 52-bit long. So in this way, we can represent any number into double precision representation. Next question, we have a binary number and now we have to represent this number into single precision method. So we have binary number, we don't need to convert it into binary as we did in previous example. Now we will normalize this number and we will move this binary point up to this position, to the right of the leftmost one. As we have discussed that whenever we move the binary point to the right, the negative power will increase. And here we moved this binary point up to 6th position. So we will write this number, normalized number, as 1.00011001101 into 2 to the power minus 6. Now we have normalized number. We have true exponent of minus 6. Next step is to calculate the biased exponent. Biased exponent will be calculated as true exponent plus bias. Minus 6 plus 127. We will have plus 121 and now we will convert this number into binary. So you can see that the number is negative, so sign bit will be 1. We have the representation of this given number into 32-bit representation. Sign bit will be 1. Exponent, we have calculated the biased exponent, so we will copy this biased exponent here. We will have the mantissa part, this, so we will copy this mantissa part here, and to make this mantissa field up to 23-bit long, we will add some zeros to the right. So in this way, we have represented the given binary number into 32-bit representation. The second part of this question is to represent this number into double precision representation. So as we have seen that the number will be normalized because it is already given in binary form. So normalized form of this number is this. Now we will calculate the biased exponent. In this case, the bias will be 1023. So we will have 1017. Now this number will be converted into binary number. The number is negative, so sign bit will be 1. Exponent will be copied here, and mantissa part. We will copy this mantissa part here. We will add zeros right to the mantissa to make this mantissa field 52-bit long. So in this way, we can represent this number into double precision representation. Now, what we will do if any floating point representation in either a single precision or a double precision has been given. We can see in this example here we have to find the value represented by the following floating point representation. So we have given this 32-bit representation, and now we have to find out what value is being represented by this representation. We have given this representation, and now sign bit is 0. It denotes that number is positive. We have given biased exponent this. Now we have to calculate the true exponent from the given biased exponent. Now we have to calculate the decimal equivalent of this number. So biased exponent is this. We have to calculate the decimal equivalent, which is 136. Now true exponent will be calculated as biased exponent minus bias. This is 32-bit representation. So bias will be 127. Biased exponent is 136. So we will have plus 9. And we will write the mantissa part. We will look at the rightmost one. We will note down the mantissa part up to the rightmost one. All the zeros after rightmost one will be discarded. So we will write the mantissa here. We have true exponent of plus 9. So we will write the normalized number. As we have already seen that 1 is not stored. So 1 point mantissa part into 2 to the power true exponent, which is plus 9. Now we can rewrite this number as, or we can simplify this plus 2 to the power plus 9. Now we will calculate the decimal equivalent of this binary number. So for this you must study the lecture on number system, how to convert a binary number into decimal. So we will have this decimal equivalent to this given 32-bit representation. So in this example, a 32-bit representation of a floating point number was given, and we have to find out the value represented by this 32-bit representation. So first of all, we will see the sign of the number. It is 0, so it is denoting positive. So we have put the positive sign. Now exponent, biased exponent is given. We will calculate the decimal equivalent of this bias. Next, we will calculate the true exponent. Now we have taken mantissa part from the mantissa field. Now we can write the normalized form of this number. We will simplify this number and we will convert this number into decimal number. So this is the value which is represented by this given binary floating point representation. So now we will look at some special value representation. As we have discussed before that we will always exclude the biased exponent value where biased exponent contains all zeros or all ones. When exponent contains all zeros, then it will depend on the mantissa part what value is basically being represented. When exponent value is having all zeros and mantissa part is also 0, it represents value 0. For the system it is value 0. When exponent is having all zeros but mantissa part is not having all zeros, or it is a non-zero value, then it represents very close to 0 number, because biased exponent is having all 0. It means that true exponent is minus 127 and it is added with the plus 127, then biased exponent will be 0. So 2 to the power minus 127 will be a very small number which is near to or very close to 0. So biased exponent is having 0. Here Mantissa is also having zeros, then it will represent 0. When exponent is having all zeros but mantissa is non-zero, then it represents number very close to 0. When exponent is having all ones and mantissa part is having all zeros, then it represents to infinity. In the other case, exponent is having all ones and mantissa is having non-zero value, then it represents to not a number, or we can say invalid number. So exponent of all zeros and fraction mantissa is also having zeros, then this represents 0. Exponent of all ones and the mantissa is having 0, this represents to infinity. An exponent having all zeros but mantissa having non-zero value, then this represents to a number very close to 0, and these numbers are called denormalized numbers. Exponent having all ones and mantissa is having a non-zero value or fraction, then this will give the not a number or invalid number, and these number are used to signal various exception or condition as a division by 0. Then this exception can be represented by a not a number or invalid number. So far we have discussed floating point numbers, two techniques of representing floating point numbers, in which fixed position representation and floating point representation. Then we discussed IEEE formats for representing floating point numbers, in which we studied single precision method and double precision method. And for these representation, two functions were required. One is normalization, second is biasing. So, and next we discussed some numerical example of representing one number into single or double precision representation. Next, we looked at the spatial values representation in IEEE formats. All the content of this PPT has been taken from three books. One is written by Sir William Stalling, second by Sir Karl Hamacher, and third by Sir Morris Manno. So you can refer these three books for floating point representation. Now we will see you in the next lecture. Till then, happy learning. Thank you very much.